Hello, I'm Alex Mazarski. I'm a fourth-year electrical engineering technology student, and I am the Avionics team lead of Payload.
My name is Dean O'Brien. I am a third-year Mechie, and I am on Avionics Structures.
Hi, my name is Braxton Crandall. I'm a third-year Mechie, and I'm on Integration and Recovery.
So we're going to run through our presentation for you. We're going to start with our requirements, get into our design, go over some analysis, and then hit our timelines.
For the concept of operations for the payload, our primary mission this year is to deploy an inflatable module that contains an antenna at least 1.5 meters above ground level. To achieve this, after descending under parachute, the payload will use servo-actuated flipper arms to rotate itself so that its back metal wall is facing towards the ground. In this diagram, it's the purple wall. Once it is flipped over, the front door will unlatch using the same flipping mechanism that flipped it over, and a pump will begin to inflate the module up to full height.
We're going to get into our requirements. One of the biggest requirements that Ezra has put on us this year is that now the payload has a minimum weight of 2 kilograms as opposed to previous years when the minimum weight required was 4 kilograms. Additionally, they changed the maximum speed at which we can hit the ground, which is now 11 meters per second. One of the biggest requirements we are implementing on the payload is that the inflatable module antenna must extend over 1.5 meters above the ground so that we can clear any potential ground coverage that is out in the desert in Texas. And then these are just our interface requirements to make sure that we fit in with the rocket and everything goes together correctly. This is our budget. Our total budget is supposed to be around $1,200, with our biggest spending coming from the servo motors and the Control Freak SRAD Avionics board.
So for the frame structure of the payload, it's changed from previous years. It's changed from previous years to have more of a C shape with a solid aluminum back wall instead of frame with posts. The main purpose of this is to move the center of gravity closer to one side to make it easier for the servos to flip, as well as keeping the front open for anything that needs to happen with both the servos and the module. For the mission bay, which is the area contained by the aluminum plates, the top has our servos, which will be flipping the payload, and the pumps for inflating the module. That center area is area reserved for the module. It's not in this image for clarity, but it will pack into that area. And in the back, there will be a raceway that runs up to all the servos and pumps from the Avionics section. And the Avionics section has all of our electronics, both cameras and control and GPS locators, as well as all our batteries. For the self-righting system, like I said previously, the servos actuate a flipping arm that can prop it up and push it over onto another side. If it lands on the front, there will be a series of 2 servos that will flip it over onto the back. The mission bay door will be hinged open to allow the module to escape. This will be pinned down by the front servo that will hold it down during flight. Once the servo actuates and is moved out of the way, the mission bay door will be free to open on its own, whether that is from the forces of gravity as it's moving or from the module inflating and pushing it out of the way. The parachute bay, also different from previous years, it will be made of printed PETG. It will also incorporate a 900 megahertz antenna for our featherweight GPS tracker. The main design behind this is to keep it out of the way of the major interference the frame can cause and get as little in the way of that antenna as possible. For the module, it will be a blown plastic film LDPE bag, which is heat sealed to make a bladder. That will then be wrapped in a Tyvek liner to help keep it safe from any debris or thorns or any possible risk for popping in the desert. Inside the Tyvek, but outside of the bladder, we will integrate a 433 megahertz antenna bazooka-style antenna that will be transmitting and helping and trying to validate the mission.
For plumbing for our module, we have two 1.8 liter per minute air pumps that are slotted in between our servos. They connect via 3mm surgical tubing to our manifold. The manifold integrates the pressure relief valve into the system, allowing excess air from the module to actually exit the system and protect the module from overfilling or popping. We're going to use SLS to make this manifold because with that pressure relief valve uses very small NPT threads, and it's not really feasible to make that with FDM. For our Sabot, we've had 2 brake tests since the CDR, and it gave us really useful information such as where we want the shock cord to run, how much shock cord we want to use, and how much tension we want to have in each leaf, what knot types to avoid, and how we want to use super glue to connect the leaf halves to create an intentional breakpoint. Some things that recovery mentioned it earlier. We want to test to make sure that this won't this will be safe for deployment, and we also need to still test our screw switch guides for comfort for whoever's arming the rocket. For the Sabot interface, we're reducing the total amount of holes in the rocket body by using the alignment pinhole as a vent hole, as well as the arming holes. On the left there, you can see the Sabot is pinned for arming. It can't move rotationally or vertically in the rocket. This will align our screw switch holes and allow whoever's on the ladder to arm the payload. Once the pin has been removed, the Sabot will shift down the tube and be resting on that coupler, and the arming / pinholes become vents.
For the Avionics section, it is going to all be contained within that lower section of the payload. There are 2 parts to this. There's the main structure, which is holding our batteries and will act as protection and a structure for the sled. That sled will contain all of the hardware that we need, including our custom SRAD board and our GPS trackers. This is designed to be able to slide out of the structure for easy maintenance on any part of the electronics. The structure will hold a 5 amp hour 2S battery for the control freak board and a 3.5 amp hour 1S battery for the featherweight. The sled will have both of our cameras, our featherweight GPS tracker, our GPS antenna for the control freak board, both of our screw switches, and power in from the batteries so that it's all nice and neat and wired up. The cameras, we will have 2. One will be in a vertical orientation with the intention of watching the module as it inflates to ensure that it opens successfully, and if there are any problems, we can try and diagnose anything that may have gone wrong. We will also have a downward-facing camera, both for a more scenic view of descent and also to assess where the payload landed, how it landed, and to give us context into any possible failures or successes.
Getting into the custom SRAD Avionics board, this year is the Control Freak. The mission of Control Freak is to power the servos that will be riding the payload on the ground, power the pumps that will inflate the inflatable module, control the cameras, and then also control the GPS coordinate receiving as well as transmitting of those through the antenna in the inflatable module. Quick overview of a list of the main parts we're using for this. Go over it more in the high-level wiring diagram. You can see we're using the STM32 as our microcontroller. Some of the bigger things to point out, we have our Max M10M GPS chip that's connected via UFL connector to the patch antenna we have for it. And then the RFM98 chip, which is our radio chip, is also using UFL connections to connect to our custom antenna that will be inside the inflatable module. We have 5-volt logic level shifters to control the logic for the servo motors, and we have 5-volt load switches controlling the cameras as well as the air pumps. Gesundheit. For our batteries, we're using a 2S Li-ion battery with 5,000 milliamp hours that will go to the Control Freak and then will then be split up into the 2 cameras, the 3 servos, and the air pumps. And we also are using a coin cell battery that will just be used as the backup voltage for the GPS chip. And what that allows us to do is that allows us to turn on the control freak board in the pits, and we can get everything set up and allow the GPS chip on board to get locked with satellites. And then we can turn the board off to save battery, and the coin cell battery will store the RAM of the chip when the chip was last on, so that when we power the board back on up on the rail, it will hot start the chip and it should get locked immediately, letting the GPS chip work perfectly. And then we have a 1S Li-ion battery used that's just to power our featherweight tracker. Cool. So these are some of the mission risks that could affect our ability to complete the mission. Sorry, I was just given these. One of the big ones is that the door of the payload will not open, or the payload lands face down and doesn't flip itself and can't get itself off of the front face. We are hoping that the air pumps will have enough force in them when they are inflating the inflatable module to push that door open, as long as it is unlocked by the servos, and help right the payload itself to get it up in the air. Another mission risk of ours is that the inflatable module gets punctured by a bush or thorn or something out in the desert, which is why we have covered it with the Tyvek shielding around the edges to give it some damage resistance. And also we have a air relief valve, or a pressure relief valve, so that way it doesn't get too pressurized and is more likely to break from contact with something. We also have the risk that one of our pumps does not work, which is why we are using two pumps together, running at 50% duty cycle, one on, one off, one on, one off. That way, if one of them doesn't work, at least the other pump will still be pumping air into the inflatable module.
For the time to fill for our module, we calculated a time of about 2 minutes. Something to note is that the geometry used in this calculation is different to the one we most recently tested. That module that we tested actually took 6 minutes to inflate. So my assumption right now is that it's going to be sometime between those two for the new geometry. As for torque requirements for the flipping system servos, we have about 5.5 kilogram centimeters. Our servos are each rated to about 18, so we're not really concerned about that. For descent velocity, we just use the drag equation at 1,500 feet above ground level, which is where that requirement is set. We are moving at 10.74 meters per second. As for snatch force, we used accelerometer data from last year's cameras to kind of just take a big overestimate. We generalized that acceleration during the deployment event at about 100 meters per second squared. We took the mass of the payload last year at 4 kilograms, and we just got 400 newtons. This is much more than we actually expect to see, given that our payload is about half the mass, but it's a good overestimate to shoot for safety. As such, we did FEA on our top plate to make sure that it wasn't too thin and wouldn't get snapped whenever the snatch event happens. And we have a minimum factor of safety of 3.5 with the stress concentrations understandably at the point of the eye bolt and at the corners where the connection to the rest of the frame happen.
The mass budget for this year, most of the mass is made up with the frame, mostly in the aluminum. Most of the mass is made up with the frame, and the second largest portion will be the Avionics section.
Going over the Control Freak Avionics board with our batteries, the Featherweight and the SRAD Avionics board Control Freak will both be turned on in the salvo queue, with the exception of the coin cell battery, which will be powering the GPS chip, just the backup voltage pin to store the RAM once assembly happens. The cameras are both powered on with boost detection. the upward-facing camera will be recording for 35 minutes, and the downward-facing camera will be recording for 13 minutes. And then the servos will be powered on once we detect that we have landed, and will run for approximately 1 minute combined. For capturing data, the featherweight and the GPS chip will not be capturing data that gets saved until boost is detected. Along with that, our high rate telemetry will start during boost until we detect landing, and then we'll just collect some low rate telemetry. And then our upward facing camera will be recording for 35 minutes, and our downward facing camera will be recording for 13, starting with boost. Looking at our batteries, our peak current draw from our 2S Li-ion battery is at 7.86 amps, which is a very large and scary current draw, but that is a very unrealistic representation of what this will be pulling. We'll break that down on the next page. We ended up getting a battery life of around 29 hours looking at what everything will actually be pulling current-wise. And then for our featherweight, we just have, it has a maximum pull of 112 milliamps, and we have a 3.5 amp hour battery, which gives us a 31-hour battery life for our featherweight. Looking at the power budget breakdown for our 2S Li-ion battery, you can see that the biggest offender of current consumption is our servo motors with 6.6 amps of current draw during stalling. But obviously our servo motors will not be stalling the entire time that they're running, and they will not be running for very long anyways. And along with that, having a maximum pull from the pumps and from the cameras are both only on for short periods of time. And once we broke all of that down, we got the capacity consumption for each component and added those together to get 5,000 milliamps of our battery, which gave us that 29-hour battery life. For collecting data, you can see that we're only collecting GPS data at 1 hertz. That is so we can run our GPS chip in its lowest power setting and keep current consumption to a minimum. And we are pulling accelerometer and gyro data at 1 kilohertz, and that's just to get some fine resolution on that data during boost. So for some of our manufacturing, we want to have all of our 3D printed parts done by the end of February. As we're approaching the finalization of all of our frame designs and everything, that should be completely manageable. As well as we want all of our frame pieces milled right at the start of March. We have all of our stock in for that, so we should be able to jump right into manufacturing all of that. And then for our Control Freak Avionics board, as we mentioned earlier, layout is almost complete with that, and we're hoping to have that in by the end of spring break so that every hand soldered component can be added to that, and they can be given to software to begin software development on the board and testing. For some tests, we want to test the Sabot, make sure that the Sabot will deploy from the rocket correctly. We want to make sure that the bladder will inflate and see how long it takes for the bladder to inflate inside of the module, and also how quickly it loses its pressure, so we can have some more strict data on that. We want to do some testing with the inflatable module to see how any sharp objects from bushes or trees or the ground will affect the Tyvek like protection around it once it is pressurized all the way, to make sure that it will not break from bushes or anything. Once everything is put together, we want to make sure that the payload can self-right itself with all of the mass accounted for inside of the payload. I think that covers all of our tests. So now we are going to cover the payload detag change. So Monday evening, we got an alert from Ezra that they have updated the detag to include the rule that payloads must comply with dual event deployment recovery systems that the rockets do, and that the line in the detag that says payloads are exempt from all dual event recovery requirements was supposed to be taken out. Seems like a bit of an oversight, but that happens. So now we have to design our payload to take in account for a dual event recovery system, which there was not a ton of room for, but we have worked on. So our plan is to implement a reefing system, very similar to last year's reefing system, using two RRC-2Ls as the flight computers and two Piranha cutters. And you might be thinking to yourself, but last year you guys had issues with the reefing. The fire wires ripped out because the lines were too short. Correct. That has been rethought and redesigned so that the Piranhas are just around the eye bolt and then has a line coming off of it so that there is no issue with the length of the line. And then the Piranha cutter will just be set off right around the eye bolt, which will release the line and disreef the parachute once we are at 1,500 feet above ground level. Where are we going to fit all of this? We are going to house the two RRC-2Ls at the very bottom of the parachute bay, above the plate, like level with the eye bolt that will then be covered by PETG, and then the batteries will be protected in the corners around it so that all of the recovery avionics are contained in the parachute bay. And since the payload can weigh less this year, the parachute is smaller, which gives us the room to fit all of us in there. The reefing system, we're going to have two loops around the skirt of the parachute that will have a thin Kevlar line routed through it and then down, tied together on the one reefing line. So that way, when the Piranha is cut, it extends like that and allows the parachute to open up the rest of the way, which satisfies the dual event recovery system. This is a revision of our COTS wiring diagram. You can see that the featherweight connectors, or the battery through the featherweight has stayed the same, and we have just added two 1S 500 milliamp, two 1S 500 milliamp hour batteries that connect to the primary and secondary RRC-2L, that connect to the firewire, that connect to the primary and secondary Piranha.